Welcome, dear students. In the last class, I was discussing on the pressure compounded impulse turbine and its corresponding performance parameters like the nozzle efficiency, etc. So I will continue from that. Now, I was discussing here that in the pressure compounded impulse turbine, basically, as we can see that there will be basically for all the stages, means for all the moving blades, the entry of the moving blade, there will be the same velocity of steam. So for say this is stage one, the velocity is v1, means as it is means given the names. So at the entry to the moving blade, the names of the speed of steam given as V1, and at the from the exit from the blade, the names are given as V2. So that is usual nomenclature. We are following that, but we will keep in mind that for each of the stages, that same nomenclature we will just continue. But there, as we have done in case of say velocity compounded impulse turbine, so that kind of nomenclature may also be means considered or adopted. Okay, like what you have to follow is that say the green colored stage is a stage one. So in this stage, in the nozzle there is a pressure drop, and in the blade there is only change of velocity as it is expected, because this is the impulse turbine. So there is only change of velocity of the steam. So the blade is getting the momentum and the steam is losing its momentum. Therefore, the steam velocity drops and blade is gaining its momentum. But here, as usual, the blade speed is not shown. Therefore, there is no question of depicting the momentum of the blade. Only the momentum of the steam is shown. So that is here you can see that this line, that is a long dashed dotted line like a center line. So here the velocity drops again. Here the velocity will increase due to the pressure fall. So please follow the steps one by one. That means the green is stage one, then this little blue, light blue color. So that is stage two. Again, the magenta color, that is stage three. So one by one, you please follow the stages one, two, and then three. In stage one, there is a pressure drop in the nozzle, that is this nozzle, fixed nozzle. Then in the blade passage, there is no pressure drop, but only velocity drop. So in the nozzle stage, velocity increases due to pressure drop as the nozzle cannot move. So the velocity of the steam increases. In the blade passage, the momentum of the steam is imparted to the blades, and therefore the blade velocity increases, and as a result, the steam velocity drops, the steam momentum drops, and kinetic energy drops. Okay. So that is the usual thing that by this time you must have uh, adopted properly. That is the thing, common thing that is going on. So that is happening for all the stages. Only thing that is common is that for all the stages at the entry to the moving blade, the velocity is same. That means after the expansion, what we are basically doing here as a compounding is to be seen that in the nozzle stage there is a pressure drop. Now the total pressure drop is now actually splitted into two or three stages as it is expected. So it is here one pressure drop, then another pressure drop here, another pressure drop here. But as a result of all these pressure drops, the increment of velocity up to v1, this is same. Okay, that is the thing that is common to all the stages. Okay, so Another thing is that here, so that pressure increases. Now, in this stage, that is in the moving blade, as we draw the velocity diagrams or the velocity triangles or the compounded velocity triangles, as we see, as we do it regularly. So at the entry to the blade, the velocity is v1, and at the exit from the blade, the velocity is v2. Okay. Now there is a quantity, that means here at the end, if I enlarge it a little more, you can see this one. Say, for example, this is the end of one stage and the starting of another stage. That means the green, here one stage is completed, another stage here in the blue, the starting of the next stage. So in between, you see there is a gap. Obviously, mechanical components are there. Therefore, you cannot have two things or two moving components or one moving component, another fixed component exactly means having no gap. So that is not possible. So as a result of that, there is a gap. So you see that at this point, if I need to enlarge it a little more, you see, you consider this point. So you can see that this is the end and this is the start of the next stage. So here you see, let me show it with a color. So here you see there at this point and at this point, there are 2 points. Let me do it with a different color. This one. So yes. Now consider this orange point, orange colored point, and the green colored point. At the orange colored point, the velocity is from the outlet of the nozzle, outlet of the moving blade. Excuse me. This is the orange is the outlet from the moving blade, that is V2. And here there must be or there may be a change of velocity. So as it is shown with a horizontal line, there may be some velocity drop. Okay. So there is a quantity denoted with phi that is called the carryover coefficient. Carryover coefficient means basically at this point, say at the orange point, say the velocity was v2. Therefore, the kinetic energy is m dot, that is rate of kinetic energy is m dot v square by 2, or say kinetic energy per unit mass is v square by 2 here at this orange point. Yeah, I may give some name here so that you can follow properly. Say point here, it is say B, and the orange is say A. So at A, the velocity is v2, therefore the kinetic energy is say v square by 2, that is per unit mass. Obviously, I'm writing per unit mass, v square by 2. And at B, it is expected that the velocity should be same, but there will be a change in velocity, and the velocity definitely drops as there is no pressure change, only due to some friction, etc. There may be, although there is no mechanical component, but there is a velocity change. Okay, maybe due to some expansion or like that. So here basically the velocity will be something else, and we define the kinetic energy here at B, at point B, as it is phi of v squared by 2. Instead of v squared by 2, we write that the kinetic energy here will be phi into v squared by 2. That means a fraction of that v squared by 2 is available at point B instead of simply v squared by 2. So phi is, you can guess, as you can guess, phi is basically less than 1. Okay. phi is less than 1. So there is a decrease or reduction in the kinetic energy as a result of some drop or reduction in velocity. So from A to B, there is a reduction in velocity there will be a reduction in kinetic energy, and the fraction of that kinetic energy, that phi, is called the carryover coefficient. Phi is called the carryover coefficient. Okay, now this is same. This is true. This is basically valid for all such exit from the moving blade. That means this is valid for stage 1, valid for stage 2, stage 3, etc. So means wherever there is a change of stage, or there is a means shifting from one stage to the next stage, that phi, that is that quantity is to be means used, or that quantity is uh, better to say it comes into picture. Okay, so that was one thing that I was discussing in the last class, but due to internet failure, I could not complete. Okay, so that should be clearly understood. Next, the next thing is we will basically calculate the quantities in case of pressure compounding. So here, basically pressure compounding, I discussed in the last class, but I am recapitulating here today for completion, that phi is the carryover coefficient. It is the fraction of the kinetic energy corresponding to V2 that I just mentioned, which is available for utilization in the nozzles for the succeeding stage. So as you can understand that here, this V2 part of that kinetic energy corresponding to V2 is available for this nozzle. You see that this is nozzle. So this blue is the starting of the nozzle for the next stage, succeeding stage, and this is coming from the moving blade of the earlier stage or the previous stage. So that part of the kinetic energy that is corresponding to V square by 2, that is available for expansion in the nozzle in the next stage at B, that is called the carryover coefficient. So that I was telling, and it should be clearly understood. Okay. So carryover coefficient, it is the fraction of the kinetic energy corresponding to V2. So corresponding to V2 means you can clearly understand, corresponding to V2 means basically V square by 2 per unit mass. Obviously, I am telling. So it is per unit mass. So it is this is total kinetic energy corresponding to V2. That means with mass flow rate m dot per unit mass, it will be basically V square by 2. V square by 2, and therefore the part of that kinetic energy that is available is therefore phi into V square by 2. So here that phi is the carryover coefficient. That means the energy that carries over to the next stage of the nozzle for expansion, or further expansion. That means from V2, it will again go to V1. That means in the nozzle stage, there will be a from V2, there will be V1. That means it will go from I'm sorry, it should be V2. So in the nozzle stage, there will be a change in velocity, that is increase in velocity from V2 to V1. As usual, what we consider is that for the first stage, there is as if from zero velocity, you can see clearly, you can see. Okay. So this picture I am showing from the book by W.J. Kearton. That is a nice book on steam turbine. W.J. Kearton. একটু একটু পরে বলছি, একটু পরে। This picture, this diagram I have taken from W.J. Kearton. The book name is Steam Turbine. theory and practice. This is an old book, maybe some Indian uh, versions available now. Okay. Yes, please, Shovik. Yes. Carryover coefficient, should I repeat? Okay, okay. So as you can see that you see that consider two stages. As I was telling, say the stage one is colored with green, light green, and the stage two is colored with light blue. So when the steam is leaving stage one and going to stage two, okay, now you see that there is means it is expected that it will go with the same velocity as you can see that there is no change in velocity here. Okay, as you can see here for this there is no change in velocity. This center line, that means the long chain dash line is showing the velocity variation. So here you see that as it comes from the fixed blade, sorry, moving blade, and after that there is no change in velocity within this passage. Within this passage means in this gap between the stage one and stage two, there is no change. It is ideal case. Okay, but actually what happens that from this velocity, from the outlet from the stage one and to the inlet to the nozzle of the stage two, there is a change in velocity. So that change is given by a coefficient called the carryover coefficient phi. That means as if at the end of stage one, the velocity is V2. The velocity is V2, therefore, the kinetic energy per unit mass is V square, V2 square by 2, isn't it? And at say point A, it is V2 square by 2. But at point B, ideally it will be V2 square by 2 itself. But actually it is not V2 square by 2, it is a fraction of that. That means there is a reduction. So that factor is called the carryover coefficient. That means at point B, the kinetic energy of the steam per unit mass is phi into V2 square by 2 instead of V2 square by 2, where phi is less than 1, say about say 0.9, 0.95 like that. So phi is not that low from 1, it is quite close to 1, like say 0.95, 0.94 like that. Okay, it is very close to 1, but it is not exactly 1. There is a reduction. So that is called the carryover coefficient. Okay. Okay, sir. Okay. Now, accordingly, the calculations will be actually in terms of carryover coefficient, because for all the stages there will be reduction, means due to this carryover coefficient, because as it is reduced, some loss will be there, so it will be carried over. It means for stage one to stage two, from stage two to stage three, so that loss will be, means that loss will uh, be lost forever. That is why that will remain in the calculation. Okay. So let us see the calculation. So you see that that was discussed. Now V2 is the absolute velocity of the steam leaving stage one, and therefore corresponding kinetic energy is m dot V2 square by 2, that is rate of kinetic energy obviously, and phi is the kinetic energy from the next stage divided by m2 V2 square by 2. Therefore, kinetic energy for the next stage will be phi into m dot v2 square by 2. That I was telling. It should be clear. Kinetic energy for the next stage is equal to half phi into m dot v2 square by 2. Okay. Another thing is here, one thing we can write is that, say for example, exit from the nozzle. Say for example, if we write a energy balance between the exit from the nozzle in the next stage and exit or inlet to the nozzle in the nozzle in the exit to the, sorry, inlet to the nozzle. So that can also be written like this. Okay. So say for example here, what is the velocity? So V1 is the exit velocity from the nozzle and V2 is the inlet velocity to the nozzle. So therefore corresponding enthalpy is say H1 and then H2. Therefore we can write V1 square by 2 plus H1 is equal to V2 square by 2 plus H2. It is to be remembered that this is adiabatic situation. It may not be isentropic. So this is for adiabatic flow.
The V2 square by 2 plus H2 এটা কি foreign nozzle inlet?
Inlet to the nozzle, huh? Now actually it should be phi 2. Actually, in actual situation it should be actual situation it will be 5. Actual situation it will be 5. It will be multiplied with 5. Ideally it is like this. Okay. Ideally it is like this. Actually it should be multiplied. V2 will be multiplied with 5. So there is already a loss.
Okay, sir.
Okay. Now another thing that nozzle efficiency is defined for this as nozzle efficiency. Nozzle efficiency. So what is that nozzle efficiency? Nozzle efficiency is defined as increase in kinetic energy in the nozzle. Okay. Divided by the isentropic enthalpy drop or adiabatic enthalpy drop. Increase in kinetic energy in the nozzle divided by the adiabatic enthalpy drop or heat drop. Okay. So Now, therefore, for the nozzle, what is that? I said increase in kinetic energy. So in the nozzle, what was the inlet kinetic energy for the nozzle? So increase in kinetic energy means basically what? Means from the inlet to the exit. What is the increase in kinetic energy? So increase in kinetic energy means basically, say we can write delta Ke. Both say we are writing per unit mass, and in the denominator we have basically delta H, isentropic or adiabatic. Now what is delta Ke? Basically from inlet, what is the velocity at the nozzle? Actually it should be pi into v2 square by 2, and at the exit it should be v1 square by 2. So change is equal to basically increase is equal to v1 square by 2 minus pi v2 square by 2. That is the increase in kinetic energy in the nozzle divided by adiabatic heat drop, that is this. Therefore, we can write the nozzle efficiency as equal to v1 square minus pi v2 square by 2 delta H adiabatic. So this is the nozzle efficiency. Again, the gross stage efficiency uh, is equal to nozzle efficiency multiplied by the blade efficiency. That is usual for all the stages. So that remains the same. So the stage efficiency or the gross stage efficiency, or this is also called gross stage efficiency, same, is equal to the nozzle efficiency multiplied by the blade efficiency. So this is called the stage efficiency or the gross stage efficiency. So that is okay. Now there are other calculations uh, that can be done, but I do not know whether that is there in the syllabus. So means rigorous calculation of uh, the enthalpy drop and the corresponding gross stage efficiency. That calculation can be done, but it will take some time. That is actually that requires okay. That is up to this. Now, if we can follow the calculation. So, hello.
হ্যাঁ স্যার বলুন।
একটু
হ্যালো স্যার বলুন।
বলছি। Okay, so we have calculated that part, and there is one a long calculation that I will separately record and upload in a video. So that requires a little involved calculation regarding the uh, change of stage. That means from one stage to another stage, the velocity diagrams and related calculations of nozzle efficiency, that I will separately take a class and then I will share. Okay. Now, so this part is completed regarding the pressure compounding and related uh, quantities related to the performance of the pressure compounding of the impulse turbine.